Today we're diving deep into a topic that, while scientifically fascinating, also carries immense real-world implications, especially for communities living near volcanoes. We're going to explore lahars, specifically those incredible yet incredibly destructive lahars formed from pyroclastic flows, and how they can extend danger far, far beyond what we typically think of as the immediate eruption zone. You see, when we talk about volcanic eruptions, our minds often jump to explosive blasts, towering ash plumes, and scorching hot lava flows. And yes, those are absolutely devastating. But there's a less understood, yet equally terrifying, hazard that often follows, sometimes long after the initial eruption. Lahars. Imagine a fast-moving river of mud, rock, and volcanic debris. That's a lahar. They can be incredibly powerful, carving new paths through valleys, burying towns, and destroying everything in their wake. Now, not all lahars are created equal. Some form when heavy rainfall mixes with loose volcanic ash on a volcano's slopes, sometimes years after an eruption. These are dangerous, no doubt. But the ones we're focusing on today are particularly potent and unpredictable, those directly linked to pyroclastic flows. For those new to volcanology, a pyroclastic flow is essentially a superheated avalanche of volcanic gas, ash, and rock fragments that rushes down the sides of a volcano at incredible speeds, often hundreds of kilometers per hour. They're devastating in themselves, incinerating everything in their path with temperatures sometimes reaching over 1,000 degrees Celsius. But here's where it gets even more complex. These flows aren't just hot. They're also incredibly energetic and often laden with vast amounts of fine-grained volcanic material. When a pyroclastic flow encounters water, and this is key, it can transform. This water could be anything from a river, a lake, or even a glacier or snowpack on the volcano's summit. The intense heat of the flow rapidly melts the ice or flashes the water to steam, incorporating it into the dense, turbulent mass. This sudden injection of water into the hot ash-rich flow creates a supersaturated slurry, rapidly turning the pyroclastic flow into a lahar. It's like hitting a turbo button on an already catastrophic event. What makes these pyroclastic flow-generated lahars so uniquely dangerous? Well, for starters, their formation is incredibly rapid and often occurs right at the peak of an eruption, when conditions are most chaotic. This gives people very little time, if any, to react. Secondly, because they originate from the high-energy pyroclastic flow itself, they inherit a tremendous amount of momentum. This means they can travel much faster and much farther than lahars formed purely from rainfall. Think about it. A pyroclastic flow can extend several kilometers from the vent. If it then transitions into a lahar, that lahar doesn't just stop where the pyroclastic flow ended. It continues to surge downstream, following existing river valleys, gaining mass and momentum as it incorporates more sediment and water. This is why the danger zone for these types of lahars can extend tens, even hundreds, of kilometers away from the actual eruption site. Areas that might feel safe, far removed from the visible ash plume or lava, can suddenly be engulfed. A classic example of this devastating phenomenon is the 1991 eruption of Mount Pinatubo in the Philippines. While the eruption itself was massive, it was the subsequent lahars, many of which were related to pyroclastic flows and later exacerbated by typhoons, that caused the most widespread and prolonged destruction. Entire villages were buried, and landscapes were reshaped, not just in the immediate vicinity of the volcano, but far down the river systems. The sheer volume of material mobilized by these lahars was staggering. Another powerful illustration comes from the 1985 eruption of Nevado del Ruiz in Colombia. Though not directly a pyroclastic flow turning into a lahar, the eruption produced pyroclastic flows that melted glacial ice on the summit. This melted water mixed with ash and debris, generating colossal lahars that cascaded down the volcano's slopes and into river valleys. One of these lahars traveled over 100 kilometers and tragically engulfed the town of Armero, killing over 20,000 people. This event stands as a stark reminder of how water interaction can transform volcanic hazards. The implications for hazard assessment and community planning are huge. For scientists and emergency managers, understanding the potential for pyroclastic flows to transition into lahars is critical. It means that traditional hazard maps, which might delineate zones for ashfall or lava flows, also need to intricately map out potential lahar paths, factoring in hydrological networks, topography, and the volume of eruptible material. This isn't just about drawing circles around a volcano. It's about understanding the entire watershed. We need sophisticated modeling that predicts not just where a pyroclastic flow might go, but where it might encounter water, how much water, and what kind of lahar it could then generate. This involves a multidisciplinary approach, combining volcanology, hydrology, and geology. For students and educators, recognizing this specific hazard is essential for a comprehensive understanding of volcanic risks. It highlights that volcanic dangers are complex and interconnected, not just isolated events. It also underscores the importance of geological research, remote sensing, and continuous monitoring of active volcanoes. Early warning systems, for instance, are not just about detecting tremors, but also about monitoring changes in river levels and sediment loads which could signal an approaching lahar. So what can we take away from this? First, pyroclastic flows are incredibly dangerous on their own, but when they interact with water, they can become even more destructive, transforming into high-energy lahars that extend the danger zone dramatically. Second, these lahars move incredibly fast and can travel vast distances, impacting communities far removed from the volcano's summit. And third, effective mitigation strategies require a deep, nuanced understanding of these processes, robust scientific monitoring, and well-communicated hazard maps and evacuation plans. It's a powerful reminder that while we can't stop nature, we can certainly learn from it, prepare for it, and work to protect lives. Understanding these complex geological interactions is a testament to the scientific endeavor and our continuous effort to live safely on our dynamic planet. Thank you so much for joining me on this deep dive into volcanic lahars. If you found this information insightful, please give this video a thumbs up, share it with your friends, and don't forget to subscribe to the channel for more fascinating insights into geology, science, and the wonders of our natural world. We've got so much more to explore together. Until next time, stay curious and keep learning.